Hello everyone. Alright, we're going to do the section 2 on power now. So if you think about power, probably most likely what's coming to your mind is basically what comes out of an outlet. Alright, now what comes out of an outlet is actually electrical current. And electrical current can do a lot of things, including work. Alright, and that's really what we're measuring when we're measuring power. We're measuring the amount of work that something does, but we can kind of think of it as like the rate at which work is done. So power is the amount of work that something does in a given amount of time. We can also think about it as the rate in which work is done. So when we see this equation, power is equal to work divided by time, alright, it's basically it. It's kind of like a velocity for work in a lot of ways, alright. So P is power, alright, capital P is power. We're going to measure that in watts, alright, and so wattage, again, you kind of think of electricity when you think of this, because if you look on all of your light bulbs, it gives you a certain wattage rating, alright. Wattage is basically how much energy is flowing through that thing to make it work, alright. So since we're talking about an amount of work in a certain amount of time, we're talking about energy in a certain amount of time. And so what a watt really is, it's a joule per second, alright. So watts is just another name that we give that, but joules per second is really what those units boil down to, alright. Power can also be measured by horsepower, alright. So this harkens back to many years ago when we did measure how much work could be done in a certain amount of time by how many horses it would take to do it. Boy, that's amazing, isn't it? You know, what's even more amazing is that most countries use watts to measure power, even for cars. Alright, so instead of horsepower for engines, you would see wattages for engines. And if you have any cool car magazines like I do, then you know that that's usually the case. They'll give it to you in both. So 1 horsepower can be converted, alright? This is exactly 745.7 watts if we wanted to convert back and forth from watts to horsepower. So there's not much going on here, guys. We're talking about a rate in which work can be done. So everything that we're going to do, if we're talking about power, work, and time, we're going to pull in all of the different equations that we can use for all these things when we're doing our examples. So let's get right into these examples, alright? So let's start with an engine of a car, alright? And this car does 148,600 joules of work. And you're thinking, wow, what a giant number. It really, really is. Joules are not a very giant unit of measurement. And so we tend to have a lot of joules when things are really, really big, alright? So we want to do two things here. We want to find the power of this engine, and we're going to calculate it in watts. And then we'll take that power and then we'll convert it into horsepower to see something that we would be more used to. Alright? So it does all this work, this 148,600 joules, in 1.2 seconds. All we have to do is use our power equation. So this right here, 148,600 joules of work. Alright? So joules, remember, measures energy. This is how much energy is being transferred or converted. Alright? So we'll start with that. The work here, 148,600 joules. Okay. We also have a time here that it takes to do this. That's 1.2 seconds. Alright. And we're looking for power. Now when we calculate this with joules and seconds, we're going to get watts, because watts are joules per second. Notice also that the units, watts, is also a capital W. So you have to be really careful here that you know the difference between your variables, like capital W for work, which is measured in joules, and then W, which is a unit, which is watts for power. Alright? It can get a little fuzzy sometimes if you're not careful. So my equation is simple. Power is work over time. Alright? So I'm looking for my power. I get a work of 148,600 joules divided by my time of 1.2 seconds. Alright. And when I do this, I get 207,167. and this is watts. Alright? So what this is measuring is how much work this thing can do in a certain amount of time, how much energy it can transfer to this car. Alright? This is watts, and when we look at that and we go, that's kind of crazy, that's big, right? So what do we do with this? What would this be in horsepower? So if I were to take this engine and we were thinking about it in English units, what horsepower would this be? So we would convert it. We have 207,167 watts. We know that there is 745.7 watts for every 1 horse. Alright. We could quickly calculate that and we get 278 horsepower, which is a pretty awesome engine, by the way. It's outstanding. So 278 horsepower, something that we're a little bit more familiar. Same thing as 207,000 watts, roughly. And that's what we're really talking about here. How much work can something get done? So you might be saying to yourself, all right, if that's as hard as it gets, that's easy stuff. Well, it could get a little bit more difficult. All right, so here is probably the toughest problem that you would be asked to do as a part of a power problem. All right. So here we have a 2,000 kilogram car accelerating from 0 to 27 meters per second in 6 seconds, and we want to know the horsepower of the engine. All right. So if we look immediately, we have a mass, we have 2 velocities. All right, a mass, 2 velocities, and a time, none of which are work, right? So here's what we're going to need to do. We're going to need to find work. To do that, we're actually going to have to find our acceleration first. And let me show you why. All right? So we know that power is equal to work divided by time. Well, I'm not given the work immediately, so I'm not given the number of joules. That means I'm going to have to calculate it. And we have one equation right now that we use, FD cosine theta, all right, to find our work. But again, we don't have a force here, right? It's not telling us how many newtons worth of force this car is pushing with, or this engine is pushing with. So what could we possibly do? Well, here's the other thing. Force is also equal to mass times acceleration. All right? So if we find the acceleration, and we know the mass, and we also know the distance that this thing travels, then we should be able to find the work, divide that by the time, and find the power. All right? Now here's another thing that I'm going to do. The force that the engine is pushing with is going to be in the same direction as what we're moving in. And so that means that our angle theta is actually going to be 0 degrees in this case. So if I'm drawing some kind of diagram, the car moves to the right, the force of the engine pushes to the right, so theta is going to be 0 degrees. And we know that the cosine of 0 is just 1, and so what we can do is erase this part of the equation. So this is the equation that I'm going to want to use for work. I'm going to use mass times acceleration times the distance. Yeah, that's mad W. I like that. That's good stuff. All right. So we need to find our acceleration and we need to find our distance. And the only way that we can do this is by solving for them using the kinematics equations. All right. So we'll start by solving for acceleration. All right. So acceleration, I have initial velocity, I have final velocity. All right. This is my initial velocity, this is my final velocity, this is my time. All right. So I'm going to use this. I know that acceleration is equal to final velocity minus initial velocity divided by time. This is one of our kinematics equations. All right. So I'm going to use that. And substitute my numbers. I have 27 meters per second. All right. Sorry, this is a minus 0 meters per second. All right. Over a time of 6 seconds, we get an acceleration of 4.5 meters per second. All right. So that's one of the things that I need. What's the other thing that I need? I need the distance. So I'm going to use that too. I have initial velocity, final velocity, and time. This time I'm going to solve for distance. So distance is kind of the same as displacement, and it's going to be in this case. So I'm going to use the fourth equation. And I'm going to use that to solve for my displacement, all right, which is going to be the same as my distance. All right, so I can say, instead of displacement, we'll just call that d. All right, so we have 1/2 times 0 meters per second plus 27 meters per second times the times of 6 seconds gives us a distance of 81 meters. All right, so now I have acceleration, I have distance, my mass is given to me in the problem of 2,000 kilograms. I can solve for my work. Once I solve for my work, I can then solve for my power. All right, so up here I have my mass of 2,000 kilograms. I have my acceleration of 4.5 meters per second squared, and I have my distance of 81 meters. So the amount of work that this thing does comes out to 729,000 joules. All right. So now that I have that, I can go ahead and calculate my power. All right. That's going to be my work over my time. So I take my 729,000 joules, divide that by my time of 6 seconds, and I get my answer for power in watts of 121,500 joules. Sorry, not joules, watts. So you have to be careful. So it's joules per second, which ends up being watts here. So that's the watts, but we want it in horsepower. Boy, I am so mean, right? So what do we do here? Just like our previous example, we're going to divide by 745.7. All right. And we get 162.93 horsepower. Outstanding. So that's a pretty normal engine, under 200 horsepower. All right. It is probably a larger than average mass for a car, but there's how you do it. I just want to point out what we did here. Work can be solved for with FD cosine theta. All right. Force is mass times acceleration. These are all things that we know, but we're going to use all of them. So we might have to use the kinematics equations to get things like accelerations and distances so that we can solve for things like work. All right. And then from that work, we can then find the power. All right, our final example here is that we have a car engine that has a power rating of 200 horsepower. All right. If the car accelerates from rest at a rate of 3.6 meters per second squared for 400 meters, what is the mass of the car? So this is similar to the last one. All right, it's actually a little bit easier. But we're going to start here. We have 200 horsepower as our power rating. We have an acceleration, all right, of 3.6 meters per second squared. We have a distance of 400 meters. This is cool. We have lots of stuff. So let's see what it is that we have and what we don't have. All right, power, 200 horsepower. If I convert this to watts, which I have to, I can't do this calculation otherwise, it's 149,140 watts. I have my distance of 400 meters. I have my acceleration of 3.6 meters per second squared. And what is it that I'm looking for? I'm looking for that mass. All right. That's cool. All right. What am I missing? It seems like everything ought to be pretty good here. Here's the problem. All right. We don't have time. Remember, power is work divided by time. And without time, I'm not going to be able to solve this problem. All right? Without time, I'm not going to be able to solve for the mass, because we're going to get that mass from the work equation. All right? So let's start by solving for time using the kinematics equations, and then after we solve for time, we can use that with the power equation to solve for the mass. All right? So we'll start with what we know. We have an acceleration. We have a distance. All right. We also know that it accelerates from rest. So we know that our initial velocity is 0 meters per second. So we'll use this equation, delta x equals v initial t plus 1/2 at squared. All right. Remember, this is displacement, but we can also think of this as distance in these problems. All right. So our initial velocity is 0. That thing's going to go away. I have 1/2 times my acceleration of 3.6 meters per second squared, and time is what I'm looking for, right? So, distance, 400 meters. All right, that's given to us in the problem here. Solve for time. So we're going to multiply both sides by 2 to get rid of the 1/2. We're going to divide both sides by 3.6. But then remember, that's t squared, all right? So t squared is 222.22, all right? But that means that t, we have to take the square root of that. Hey, lunch is over. All right, then we take the square root of that and we get 14.91 seconds, all right? So now that we have the time, we can go ahead and put this together in the power equation to help us solve for the mass. Now I'm going to do a little trick here. I know that work is equal to mass times acceleration times the distance that is traveled. I'm just going to substitute that right into that equation there. And so I'm going to get that power is equal to mass times acceleration times distance over time. All this does is stops me from having to do two calculations. I could just do it all at once. All right? So I'll go ahead and substitute everything I know. I know my power, all right, is 149,140 watts. I'm looking for my mass. That's my unknown. I know my acceleration, 3.6 meters per second squared. I know my distance, 400 meters. Kind of running off the page there. Sorry, guys. All right. And I know my time of 14.91 seconds. So multiply both sides by 14.91, divide by 400, divide by 3.6, and we get a mass of 2,000, or sorry, oops. Sorry guys, I made a mistake. See, you can do it too. Sorry. And so we get a mass of 1,544.22 kilograms. Bam! All right. So power, it's a simple equation, but it's something that we can put into play with all of the other equations that we know. Remember, force is mass times acceleration. Work is FD cosine theta, right? Power is work over time, along with all of our other constant acceleration equations. Okay, so to kind of sum things up here, guys, let's say we have two engines, engine A and engine B. Engine A has the same power as engine B, but engine B supplies more force through it than engine A. How is this possible? So here's what we're saying. Engine B is stronger because it has more force than engine A, but they both have the same power, all right? So if we wanted to think of it in terms of watts, right, they both have the same wattage. Say they're both 100 watts, all right? So how is it that they have the same 100 watts worth of power, but let's say engine B does has twice the force, all right? So if it has 2 times the force, all right, that means it's going to do 2 times the work. So how does that work, right? If it does twice the work, that must mean that it does it in twice the time. All right? So they both have the same power rating. But engine B has more force, right? But that means that it's going to take a lot more time for it to actually do that work. All right, so it's going to have more force, but it has to have more time to make that possible. So there's a trade-off. You can have a lot of power, all right? You can have a lot of force, but time is a factor. All right, so true or false? Stronger people are always more powerful than weaker people. What do you think? Well, here's the thing. That is false. How is that false? Well, see, here's the thing, guys. You might be strong, but time is a factor. All right? So even a smaller, weaker person, if they do that work, all right, that small force, if it does the same amount of work, but it does it in less time, then you're going to have more power. So weaker people, smaller forces, have more power if they can do the work in less time. All right? And that's because power is work over time. All right? So as long as time gets smaller and smaller and smaller, then power will get bigger and bigger and bigger. So if a small person can do the same amount of work in a smaller amount of time, then they're going to have more power than a stronger person with more force. All right? So there you go. That's power. Enjoy. Have some fun on those problems. There's some tough ones that are kind of like example number 2 here, so watch yourself while you're doing them. Later, guys.